Okay, so vectors day 2. You pretty much have all the knowledge you need to solve these vectors problem, but we're going to talk about one more aspect and one more type of problem we can solve using vectors, and these have to do with navigation type problems. So navigators measure angles clockwise from the north, and this is called a bearing. Now, let's think about how we normally solve angles. So normally when we look at our axes, we start at 0 degrees and then we go counterclockwise. But bearing problems start at 90 degrees and then they go clockwise. Okay, so let's think about an angle, and let's just take the first quadrant. It would be very like the simplest case scenario. Okay, the bearing, let's just say, for a particular problem, we'll say is 75 degrees. This means from north, you would go 75 degrees clockwise. Okay. The theta, though, that we would have would be 90 minus 75, which would be 15 degrees. And this formula for finding theta, okay, which is bearing, I'm sorry, not bearing minus 90, 90 minus bearing. This is actually going to be true for all angles. So let's think about it in other quadrants. We're going to always have to transform into theta when we're given a bearing. So this is an important thing to go over. So let's think about in a different quadrant. Let's say in another problem you were giving the bearing to be 240 degrees. This means you start at north and you would go 240 degrees. So let's think about what quadrant that would put you at. That would be 90 degrees, 180 degrees. All the way here would be 270, so that would put you right here. So right here is your bearing of 240 degrees. Let's figure out what the theta should be. Okay, well, our theta is going to start at 0 degrees, and it's going to go this way. Okay, so let's think about it. It would be 90, 180, and then to find this missing part, you'd have to do a couple of different calculations. You'd have to think about how far past you were 180, then take that, subtract that from 90, blah, 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 blah. But it's going to work where if you do this theta, okay, is going to be 90 minus 240. Now I'm going to get a negative number here, but I'm going to show you how we're going to deal with this. So 90 minus 240, okay, you get a calculator for this. So if you need to use one, use one. You should be able to do this without, but you're going to get a negative number. And anytime you get a negative number, you're just going to add 360 to it and get the coterminal angle. Okay, so looking back at negative 150 was actually this angle right here. This was negative 150 degrees. Okay, but when we added 360 to it, we got 210. Okay, so that's this one right here, 210. So we get negative 150, you would add 360, and you would get, actually there's enough room here, you would get 210 degrees. Okay, and this would be the theta that you use for the resultant vector. That's what you do each time. 90 minus the bearing. If it's negative, which it will be most of the time, you're just going to add 360 to get a coterminal angle, and then you get your theta, which is 210 degrees. Okay, now let's actually use this in a problem. Okay, so number 1 says, a ship sails 20 miles along a 325 degree bearing and then turns and sails 7 miles along a 250 degree bearing. Find the displacement vector as a distance and bearing from the start. So we're given a magnitude and a bearing, not a theta, but this would be a beta. Okay, they don't get confused, theta and beta. We're given another magnitude and we're given another bearing. Okay, we need to find the thetas using what we just learned. We need to find the resultant vector, then take the magnitude, and then also find my new angle, and then turn it back into a bearing at the very end. Okay, now let me show you without converting between theta and beta. You may be thinking, well, isn't there an easier way to do this? Well, let me show you what you're left with. Okay, without converting to theta, what you would have to do is, you'd start here at 0, 0, and you'd think, okay, I'm going to sail 20 miles along a 325 degree bearing. 325 degrees would be almost all the way around. Remember, with bearings, you start at north, and so it would look something like this, and then here we'd have 20 miles. Okay, and then from here, you would have a 250 degree bearing, which would put you, south would be 180 degrees. And so, because the bearing isn't from where you're at, it's always from north. And so it puts you, about where we would be in the third quadrant. And then what you're going to end up having to do is find the distance of this and find the angle here. And that can be done. It gets very confusing, especially if you were to add even more elements into it. Okay, so let's just use what we know about vectors. And right here, I'm going to call this vector A, and I'm going to call this vector B. Okay, and so let's think about what we know about vector A. For vector A, we know that the magnitude of vector A is 20. We don't know the theta yet, but I do know that the theta is going to be 90 minus 325, and this is obviously going to be a negative number, so I'm going to have to add 360 to it. Okay, so let's figure that out. 90 minus 325, and then I know I'm going to have to do it, so go ahead and add 360. So I get 125. Okay, so that's my theta. Now this is still, an obtuse angle, so I'm going to have to, deal with that, but that's not too bad. Okay, now let's think about my other vector, angle, or vector B. So I know that the magnitude of vector B is 7, and I know that the theta for vector B should be 90 minus 250. And again, this is going to give me a negative number, so I'm going to have to find the coterminal angle by adding 360. So 90 minus 250 plus 360. I get 200. Okay, so now let's write out the components for these two vectors. I've got vector A. Remember that we're going to take the magnitude, and for the horizontal component, it's going to be cosine of my angle, and the vertical component is going to be 20 sine of my angle. Vector B is going to be very similar, except it's going to be 7 cosine 200 degrees and 7 sine 200 degrees. Okay, so I have my two vectors. Now we need to add these two vectors, and before I take magnitude, I'm just going to add the two vectors together, and let's see what we get. Okay, now I need to add these two components together. Okay, so 20 cosine, I have to do all this in the calculator, 20 cosine 125, make sure you're in degrees mode, and then add that to 7 cosine 200 degrees. Okay, and I'm actually going to store this in for A, because I might have to use that again. Okay, now for the other one, I'm actually just going to hit second enter. It's going to bring this back up, and I'm going to change these cosines to sines. And that's going to give me my vertical component, and I'm going to store this for B. So I can call up these numbers, these unrounded numbers. So let's record what we've got so far. We've got negative 18.044 for the horizontal component, and the vertical component is 13.989. Okay, that is the resultant vector. What they're really asking us for, though, is for the distance. And the distance here would be the magnitude. So I want to find the magnitude of this resultant vector. And I need to do that by taking the square root of negative 18.044 squared plus 13.989 squared. Now, I'm glad I stored these values in for A and B, because now all I've got to do is take square root of alpha A squared plus alpha B squared. Not only is this more convenient, but it's also more accurate. So I get 22.836 miles. Okay, that's the distance. That would be this distance right here. And finding the angle really isn't too bad either. It's going to take just a little bit more work, though. So let me go ahead and show you what we've got here. Now, we know that we were in this quadrant, okay? If you think about it, and I know that I'm in this quadrant not just because of my original problem, although that was a good idea. I really know that I'm in this quadrant because the horizontal component is negative 18 about, and the vertical component is positive 14 about. Okay, so I'm going to go ahead and write these numbers. Now, I know that these numbers are actually not exactly these. We'll refer back to A and B though. Okay, and here's my R, which I know to be about 23. Okay, when I say R here, I'm talking about this resultant, the magnitude of the resultant vector. Okay, so I'm just using R as abbreviation. And so let's think about what I'm trying to find. Okay, first I need to find this theta reference angle. And then I'm going to use that to find the bearing. Okay. And this theta reference angle really won't even be the true theta. So we're going to have to just think about this logically at this point. So we're going to find our reference angle the same way we did yesterday with vectors. This is going to be equal to arctan of the opposite over adjacent. Okay, and I'm going to just do 14 over 18, not the negative, because that will put me in a different quadrant that I really don't want to be in. At this point, I just want to find this reference angle, which is going to be the acute angle. Okay, so let's go ahead and do this in the calculator. So I'm going to do arctan 14 divided by 18. Okay, so that gives me about 38 degrees. Okay, but it's 37 point, oh, I'm sorry. This is not exactly accurate. What we really need to do here is arctan of my B, alpha B, and then I'm going to do that divided by negative alpha A, and I'm doing negative alpha A because A was negative, and I want it to be positive when I'm doing this. This will give me an accurate. I knew that answer seemed weird for some reason. Okay, what I had before was an approximation, but this is the most accurate because I had these values stored in. So I have 37.777 degrees. And this is still an approximation, but it's the most accurate one that I have. Okay, now to actually find the bearing, let's just think about this. If this angle right here is 37.777 degrees, the bearing is going to start at north, and it's going to go all the way around until I get to that resultant vector. So don't think, what's the rule? Just think what makes sense. If I'm starting at north, going clockwise, I'm hitting 3 whole quadrants. So it's 270 degrees. And then I'm also having to go the reference angle. Okay, so what I need to do here is I need to add 270. This is not what you're going to do every single time at the end of a bearing problem. It's what I'm doing right now because of the quadrant that I'm in. At the beginning of these problems, you can take the formula that we learned before. You can take this formula and then add 360 if you need to, and going from bearings to thetas, not bad at all. But at the very end, when you're interpreting your answer, you've got to make sure you're in the right quadrant and finding the correct beta, which is your bearing. So this becomes 307.777 degrees bearing. And this tells you what angle your resultant vector is in. Okay, this is the displacement vector. Okay, we've got our miles and we've got our bearing. Okay, if you look at the next problem, you may be thinking, oh, I don't want to go through another one of these, but really it's not too bad. If you look at all these numbers, it's the same numbers as the problem we just worked, so we don't really have to go through and redo these. But what if you notice is different is knots. Now knots is a unit for speed. So we're given a speed and then we're given a bearing and then we're asked to find the velocity. So our answer is the same number, but instead of distance, we're doing velocity. Okay, so our answer is still 22.83, what was it? Already left. 836. Instead of miles, though, this is in knots. And our bearing is still 307.777 degrees. Okay, so that's the only difference. Okay, bring your questions to class. You'll get to practice this tomorrow.